asked to talk a little bit about CP4 waves. Remember, this is just the recall stuff, so it's really important that you're able to answer all these things from memory. If you've got any issues with them, then just get in touch and I'll do my best to explain it to you. So there's something in the spec that asks us to prove that if I have got a source, for example, if it was someone's mouth, and this is my interpretation of a mouth, so sorry about that, and if we've got a receiver, so if we had something like a microphone, how can we prove that the waves, when they travel through the air, it's the movement of energy as opposed to the movement of particles? So we know that the sound waves would travel from the voice and through the air to the speaker. So how could we prove that? Well, I mean, one of the easiest things to do would be to change the paradigm, change the model. We'd have the mouth, and we could have another person with a very pointy nose. Gosh, pardon me. Another person. You could ask that one person to eat a mint or something, have something with odor, ask them to chew it, and then to speak. Now, if the person is far enough away, then the waves would travel through the air, but the particles themselves wouldn't. So we know that instead of seeing sound as these lined waves, we can think of them instead as compressions and rarefactions. Now, this is going to take a bit of time to draw, but it's worth it, so just stick with me. So there are some places where the sound waves are compressed together and some where they're spread apart. This is where we get our amplitude peaks. Okay, sorry, terrible drawing, I know, but you get the idea. Now, because the particles themselves are only oscillating forwards and backwards, then the smell of this particle won't be able to travel to the nose, but the sound will. You could also do something else, like if you had a candle and you blew the candle out so that there was just smoke left, and you again asked the person to speak through the candle to another microphone, then you'd be able to see that the sound waves would carry on through, but the smoke particles wouldn't travel all the way to the microphone. Something that's a little bit easier to do is to prove that in water waves that the particles themselves are just moving up and down, but the energy is still being transferred. So you could set up a very simple experiment with a basin of water and two things extra. You'd need a board of some description and a suitable item, so something like a bung, something that would sit in the water. What you'd then do is you'd move the wave forwards and backwards. As you did that, the water particles would start to generate a wave. You could move the wave up and down, or you could push it forwards and backwards, but you'd start to generate those wave patterns. So we'd have the waves moving forwards and backwards, and we would have the bung staying exactly where it was. You could put the bung wherever you like, and the bung is just going to go up and down. You'll be able to see the up and down movement, but we know that the energy will be moving from left to right because the board would be on the left, generating the energy. Now, another thing that we have to know is to talk with confidence about what a wave profile looks like. Now, my drawing skills are terrible, so I apologize in advance. This isn't going to be as smooth as I'd like. Okay. So there's a couple of things that we have to be able to know. We have to know the frequency and the wavelength, how to be able to tell them from a wave profile diagram. We also have to talk about the amplitude and the period. We can see those things as well from the wave profile diagram. What I'm going to do is I'm going to add on in arbitrary units. So arbitrary units will have all the way up to 1 and all the way down to -1. What you have to imagine is that there is a particle, and for this particle, it's just going to be the tip of my pen. We have to imagine that the particle is moving through space. So the arbitrary units would be the displacement of that particular particle. So if it's a transverse wave, the particle will be oscillating up and down. How far up this scale it oscillates is a measure of how much energy has been transferred to the particle, and therefore is a measure of amplitude. How far away from starting point does this object go? Because remember, oscillation means it starts in one place and it moves, but always winds up back in that place. So the amplitude on a wave profile diagram is a measure from the base to how far it moved. On the x-axis, pardon me, then we've got time. What I'll do is I'll make every one of those little dots 1 second. Okay, so 1 sec, or dashes, 3 seconds, 4 seconds, 5 seconds, 6 seconds, 8 seconds, 9 seconds. Remember that the particle itself isn't moving, but time always is. So here I've got a particle that's moving up and moving back, moving down and moving back. We would consider that one full oscillation. In this case, it has taken 1, 2, 3, 4 seconds for this particle to move from its starting position all the way back, or all the way to its end position. So that's one complete wave. If I've got one wave in 4 seconds, that means that in 1 second I would have 0.25 of a wave. That means I've got a frequency of 0.25 Hertz. Wavelength is easy. You choose 2 points on your wave profile diagram, or if you just want to annotate it, it's from tip to tip, from trough to trough, or from starting point to ending point. That there is your wavelength. The period then, I'll scribble that down here. Period is 1 over the frequency. So in this case it's 1 over 0.25, and if I'm not much mistaken, that will be a period of 4. But I'm just going to double check that because calculations in my head I was never good at. Yes. Cool. All right. We've got 2 different types of waves then. We've got our transverse waves and our longitudinal waves. Transverse waves, the oscillations are parallel to the direction of energy transfer. Longitudinal waves, the oscillations are perpendicular. Oh, pardon me, other way around. The oscillations in transverse waves are perpendicular. In longitudinal waves, the oscillations and energy transfer are parallel. Now we have to be able to name some different examples of transverse waves. So the most obvious one is light, or any other EM spectrum, any other electromagnetic wave. The oscillations, the particles moving up and down, the energy transfer going in one direction. Most common ones then for longitudinal are sound waves, compressions and rarefactions in air particles or solid particles in whatever way, longitudinal wave. Water waves are transverse waves because water goes up and down, particles don't move, the energy transfers. There's also 2 different types of seismic waves. We've got what's called push and or P and S waves, and the way to remember that is that P waves push and S waves slide. So S waves, secondary waves in a seismic event, an earthquake, are transverse. P waves, primary waves in an earthquake, are longitudinal. How to measure the speed of sound in air and ripples on water surfaces. There are 2 equations that you can use. You can use V is equal to F times lambda, or V is equal to X over T. Just a reminder then, F is frequency, lambda is wavelength, X is displacement, which is straight line distance between 2 points, and T is time. In both cases, V is velocity. Because waves have direction, they're vectors, they've got a magnitude and a direction, so we say it's velocity instead instead of speed. We can still refer to it in the speed of sound. So I'll do speed of sound in air first off. This actually came up as an exam question. It's a little bit convoluted, but really all you have to do is have a known distance, and you have to have a very accurate stopwatch. Now, you can use a stopwatch with a human being, but remember, human being reaction time is about 0.7 seconds, so it's not going to be as accurate. Instead, what you can do is have some kind of a microphone system set up to a data logger. So you would start a sound here. So the example that is often used is some kind of an explosive. So this is my interpretation of a cannon. You explode the cannon or the starting pistol, or you clap your hands, you clap two wooden blocks together, and the sound wave is generated. This microphone will log the start time. This microphone will log the time it takes for the sound to travel from the cannon to the receiver. You could also do this with a person, and this person could use the timer. So when they see the flash, they start the timer, click, the sound travels. When they hear the boom, click, that's the amount of time. If we know whatever this distance is, if it's, I want to know, X meters, and I know that it took Y seconds, then I can find the speed using V equals X over T. V would be the distance, which is X over Y, and that would give us the answer. It's a bit harder to do that if you're talking about water waves in the ocean. So instead, what you could do for that then is set up either a ripple tank or go out and have a look at the waves in the ocean. And hard to keep a distance when you're looking out to sea, so what we'll do instead is we're going to use a second equation. We're going to use V equals F times lambda. This particular wave is up against a pier or a dock or something. Doesn't really matter. All I have to do is get a timer. Okay, and I'll count the amount of waves that hit this in 1 minute. If I have 120 waves in that 1 minute of time, that shows me that I've got 2 waves per second, which is quite a lot, actually far more than what you'd normally expect, which would give you a frequency of 2 Hertz. You'd then use a camera or some kind of a scale to measure the distance between the tips of the waves. That would give you your wavelength. Say it's 10 meters. God, this is a violent storm. The velocity then would be 2 times 10, 20 meters per second. Something else we have to know then is the effect of boundaries on waves, especially in the most common thing that we talk about is a block of glass. Now, my block of glass is a dense material. The air around my block of glass is less dense. Now, instead of drawing the whole block, what I can do is just draw a as though I'm looking down on it from above. What we'll see is that, I'll use a ruler for this, what we'll see is that light, if it comes in at an angle, will move towards what we call the boundary. Okay, so this black bit here we call the boundary. Because I'm drawing a ray of light, I'm going to draw an arrow into it. My light will travel in, and as it hits the more dense material, it will start to bend. So it will move towards what we call the normal line. Now if we're going to have to do this very roughly, so I apologize for that. We draw a 90 degrees line. We call this my normal. The 90 degrees line just means if I had a light shining through in that angle, it would just go straight through without any bending. But if I add in a more dense material, if I draw in an angle, then instead of just carrying straight through my glass block, it's going to bend towards the normal. It will carry on through the block, and the interesting thing is that when it comes out the other side, it's going from a more dense to a less dense material, so it will carry on, it will bend away from the normal. Now these two lines should be going the same direction. So it goes in, bends towards the normal, as it's coming out it bends away from the normal, and it carries on in the same direction that it was going in. So simply put then, we've got this change in direction towards the normal going into a dense material and away from the normal when it's coming out. The next thing then, we've got to know about light. I was sighing there because I don't have the right colors, but what I'll do is I'll use the 3 primary colors. I'll use my red, I'll use my green, and I'll use my blue. Okay, so light is a mixture of 7 colors in total, Roy G. Biv: red, orange, yellow, green, blue, indigo, and violet. When you mix all of those together perfectly, you get a white light. If I was to pass this light through something, or aim this light onto something that's red, then something very clever happens. A red object reflects red light, which is why it looks red when we look at it with our eyes. That's why objects look red. However, green objects, or green wavelengths and blue wavelengths get absorbed, which means this red light, this red object, absorbs different frequencies of light, different wavelengths of light, and only the red is reflected. If I were to pass these 3 colors through a filter, which is a translucent piece of film usually, then the same thing would happen. Red light would go through, the green and the blue light would get blocked, and I would only have red light coming out. Which means if I put something blue in that path, it would actually end up looking black, because the red light would be absorbed by the blue object, no light would be reflected, and the object would appear black. And that, I'll leave it at that. If you've got any questions about that, don't be afraid to get in touch, and as always, stay safe, and I think what I'm supposed to say is like and subscribe.